Welcome, everyone, and thank you for joining me for today's session on cryptography and technology use cases. Cryptography is one of the foundational pillars of modern cybersecurity. It protects our data, secures our communications, and establishes trust in a world where everything is digital, distributed, and constantly under threat. Let's get started. Confidentiality ensures that information is accessible only to authorized individuals. Cryptography provides confidentiality through encryption, transforming readable data into an unreadable format unless you have the correct decryption key. Whether it's securing data in the cloud, protecting files on a device, or encrypting communications traveling over the internet, confidentiality prevents unauthorized access and protects sensitive information from exposure. Integrity guarantees that data has not been altered intentionally or accidentally. This is enforced through hashing, message digests, and digital signatures, which allow systems to detect tampering. Integrity ensures that the data we receive, store, or process is exactly what was intended, critical for everything from software updates to financial transactions. Authentication verifies who you are. Cryptographic mechanisms, such as digital certificates, public key authentication, multi-factor authentication, and secure challenge response protocols, ensure the system can confidently verify the identity of a user, device, or system. This is foundational for secure logins, secure API communication, and zero-trust architectures. Non-repudiation ensures that someone cannot deny their actions. Through digital signatures and cryptographic logging, we can prove that a message was sent by a specific party and that it has not been altered. This is essential for legal agreements, financial transactions, audit trails, and incident investigations. In short, non-repudiation creates accountability. These four principles are the foundation of trust in every secure system: cloud platforms, identity systems, secure email, financial transactions, digital signatures, and beyond. Symmetric encryption uses one key for both encryption and decryption. It is fast, efficient, and ideal for encrypting large amounts of data like storage encryption, database encryption, and VPN traffic. Algorithms like AES dominate this space. The challenge is key sharing. Both parties must securely receive the same key without it being intercepted. Asymmetric encryption uses two mathematically linked keys, a public key and a private key. Whatever is encrypted with one key can only be decrypted with the other. This enables secure communication without ever sharing a secret key. Asymmetric encryption powers TLS, HTTPS, certificates, identity verification, and many trust mechanisms. Though secure, it is slower than symmetric methods, so we typically use it for key exchange, not bulk data encryption. Hashing converts data into a fixed-length, irreversible value. Any change to the input, even a single bit, produces a completely different hash. Hashing is used for integrity verification, password storage, digital signatures, and ensuring software or files have not been tampered with. Important note: hashing is not encryption. Hashed values cannot be decrypted. Digital signatures use asymmetric cryptography plus hashing to provide authentication, integrity, and non-repudiation. A sender signs data using their private key, and anyone can verify the signature using the public key. This proves who sent it, that it wasn't modified, and that the sender cannot deny sending it. Digital signatures support secure email, software integrity checks, certificates, and many legal digital processes. Key exchange is how two parties securely agree on a shared secret key, especially for symmetric encryption. Protocols like Diffie-Hellman and elliptic curve Diffie-Hellman, ECDH, allow two systems to generate a mutual key without ever transmitting that key over the network. This is the foundation of HTTPS, TLS, and most secure sessions today. Symmetric encryption uses the same key for both encryption and decryption. That single shared key is what makes it incredibly fast and efficient, especially compared to asymmetric encryption. Because of that speed, symmetric algorithms are the preferred choice for bulk data encryption. Things like full disk encryption, database encryption, VPN tunnels, and large file transfers. Two of the most well-known symmetric algorithms are AES and 3DS. AES is today's standard, highly secure, efficient, and widely used across cloud environments, government systems, and enterprise applications. 3DES, while older, was historically used in banking and legacy systems, though it's now being phased out due to security limitations. The key point is this: symmetric encryption gives us confidentiality at scale. It's what keeps massive volumes of data protected without slowing systems down. The challenge, of course, is securely sharing and managing that key, but the encryption itself is extremely strong and efficient. Asymmetric encryption is the backbone of secure communication on the Internet and modern identity systems. Unlike symmetric encryption, which uses a single shared key, asymmetric encryption uses a public-private key pair, two keys that are mathematically linked but perform different roles. The public key can be shared openly and is used to encrypt data or verify signatures. The private key is kept secret and is used to decrypt data or create signatures. This model allows two systems to establish trust without ever exchanging a secret key, which is why asymmetric cryptography is used heavily in identity verification, authentication, and secure key exchange. Most secure protocols, TLS, HTTPS, SSH, S/MIME, and digital certificates, rely on asymmetric cryptography to bootstrap the connection before switching to faster symmetric encryption for the actual data transfer. Two major examples of asymmetric algorithms include RSA, the traditional workhorse of public key cryptography, widely used for certificates, digital signatures, and key exchange, strong but computationally heavy, requiring large key sizes. ECC, elliptic curve cryptography, a more modern approach that provides equivalent security with much smaller keys, making it faster and more efficient. ECC powers many modern systems, including mobile devices, IoT security, and modern TLS configurations. Asymmetric cryptography gives us identity, trust, and secure key exchange, critical pieces that allow the entire ecosystem of secure communication to function. Unlike encryption, hashing is a one-way function. That means once data is hashed, it cannot be reversed or decrypted back to its original form. This property makes hashing essential for security functions that don't require recovering the original data, but instead verifying that data hasn't changed. One-way functions. Hashing algorithms take any amount of input from a single character to an entire file and produce a one-way, irreversible output. This means even if someone has the hash, they cannot derive the original data. This is why hashing is used for passwords, integrity checks, and digital signatures. Hashing allows us to prove that data has not been modified. If you hash a file, message, or piece of data before transmission and hash it again when it arrives, the two outputs must match. A single bit change to the input creates a completely different hash. This makes hashing essential for verifying software downloads, logs, backups, and digitally signed documents. Fixed size output. Regardless of the size of the input data, the hash output is always a fixed size. For example, SHA-256 always produces a 256-bit hash, whether the input is a short sentence or a large database file. This consistency makes hashing efficient and predictable for storage and comparison. Two of the most widely used hashing algorithms are SHA-256, part of the SHA-2 family used in TLS, digital signatures, blockchain, secure storage, and authentication systems. SHA-3, a newer standard designed to provide strong resistance against modern cryptographic attacks. Both algorithms are collision resistant, meaning it's extremely hard for two different inputs to produce the same hash, an essential property for security. Hashing forms the backbone of secure authentication, file verification, blockchain, PKI, and many other cryptographic operations. Digital signatures guarantee that data has not been modified. When something is signed, the signer first hashes the data and then encrypts that hash with their private key. When the recipient verifies the signature, they hash the data again and compare it against the decrypted hash from the signature. If even a single bit changed, the signature fails. This ensures absolute confidence that the content is genuine and unaltered. Digital signatures also prove who created or sent the message. Because only the legitimate owner has the private key used to create the signature, successfully verifying the signature with the public key confirms the sender's identity. This is foundational for secure email, software distribution, API communication, certificates, and identity systems. Non-repudiation means the signer cannot deny having signed the message. Because the private key is only known to its owner, and because a valid signature cryptographically ties the origin to that private key, the signer is accountable. This is essential in legal agreements, financial transactions, logging systems, and audit environments. Two major technologies enable digital signatures. RSA, Reverse Shamir Adleman, a widely used asymmetric algorithm for both encryption and signatures, strong but requires large key sizes and more computational power. ECDSA, elliptic curve digital signature algorithm, a modern, efficient digital signature method based on elliptic curve math. Provides equal or better security than RSA, but with much smaller keys and higher performance. Used heavily in mobile devices, IoT, and modern TLS. Both RSA and ECDSA are trusted, standardized, and used globally, but ECDSA is increasingly preferred due to efficiency and security per bit. In summary, digital signatures provide integrity, proof the data hasn't changed; authentication, proof of who signed it; non-repudiation, proof they cannot deny their action backed by strong cryptography like RSA and ECDSA. They form the foundation of trust in the digital world. Key exchange is how two systems that have never met before securely establish a shared secret key, without ever sending that key across the network. This is what allows encrypted sessions to start safely, even over untrusted channels like the open internet. The goal of key exchange is to create a shared symmetric key that only the two parties know. This key is then used for fast bulk encryption. Key exchange protects that secret from interception, even if attackers are listening to all network traffic. Diffie-Hellman, DH, was the first widely used key exchange algorithm and is still foundational today. Two parties each generate private values, exchange public values, and independently compute the same shared secret through mathematical operations. The secret never travels over the wire, so even a full packet capture won't reveal it. Modern versions like elliptic curve Diffie-Hellman, ECDH, are faster and more secure. Every time you access a secure website, online banking, email, cloud services, the browser and server use a Diffie-Hellman-based process to establish an encrypted session. This happens during the TLS handshake inside HTTPS. The browser and server negotiate algorithms, perform DH-ECDH key exchange, establish a shared symmetric session key. Once that key is established, the rest of the session is encrypted with fast symmetric encryption like AES. Asymmetric cryptography, using public-private key pairs, is used primarily for secure key exchange and identity validation, not for encrypting large amounts of data. During a secure session, such as HTTPS, the browser and server use asymmetric algorithms like RSA or ECDH to exchange information that allows them to derive a shared secret key. The advantage is that the shared key is never transmitted, making it extremely resilient against interception. Asymmetric encryption is the trust enabler. It establishes who you're talking to and creates the foundation for secure communication. Once the shared secret is established, systems switch to symmetric encryption for the actual data transfer. Why? Because symmetric algorithms like AES are much faster and more efficient for encrypting large volumes of data. All the encrypted web traffic, file transfers, applications, and API calls you rely on every day use symmetric encryption under the hood. So the asymmetric portion starts the conversation, but symmetric encryption carries the actual payload. Certificates are the identity system of the internet. They use asymmetric cryptography and a trusted certificate authority, CA, to verify that a public key actually belongs to a legitimate server, user, or device. When you visit a website, your browser checks the site's certificate to confirm it's valid, it's trusted, it actually belongs to the organization you think you're communicating with. Certificates prove identity, prevent impersonation attacks, and ensure that key exchange happens with the right party. MTLS, or mutual TLS, strengthens traditional TLS by requiring both sides of a connection, the client and the server, to authenticate each other using certificates. This means every service, device, or API calling another must prove its identity before any data is exchanged. It eliminates blind trust and drastically reduces the attack surface. Device certificates take this a step further by uniquely identifying hardware or workloads, whether it's an IoT device, a mobile device, a VM, or a Kubernetes pod. Instead of relying on passwords or tokens that can be stolen, certificates provide cryptographically strong, tamper-resistant identity. In API-driven environments, API authentication using certificates ensures that only verified and trusted services can communicate. Encryption at rest ensures that if someone gains unauthorized access to the physical storage, disks, backups, snapshots, they still cannot read the data. Most modern systems rely on AES 256, a highly secure and industry-standard symmetric algorithm. Whether you're storing database records, object storage, or logs, encrypting at rest protects data from offline attacks, lost devices, or misconfigured storage. Encryption in transit protects data as it moves across networks between users, devices, services, and APIs. This is where TLS comes in, ensuring traffic is encrypted, authenticated, and tamper-proof. Every communication, API calls, web sessions, service-to-service traffic, should be wrapped in TLS to prevent eavesdropping and man-in-the-middle attacks. Encryption is only as strong as the system that manages its keys. Cloud platforms provide key management services, KMS, to automate secure key creation, rotation, logging, and lifecycle management. Using customer-managed keys, CMKs, gives organizations direct control over the keys that protect their most sensitive data, allowing them to define policies, rotate keys on demand, and enforce compliance requirements. Even with strong encryption, the real power comes from controlling who can use the keys. Permissions-based key access means that only authorized identities, services, applications, users can request encryption or decryption operations. This principle of least privilege ensures that data processors can handle encrypted data without ever seeing raw keys, and key misuse becomes nearly impossible without explicit authorization. Combined with IAM and audit logging, this provides a full chain of accountability. Simply hashing passwords is no longer enough. We need layered defenses that make cracking attempts computationally expensive, unpredictable, and practically infeasible. Hashing is a one-way transformation. When a password is hashed, it's converted into a fixed-size output that cannot be reversed. But hashing alone is not secure for passwords. Why? Because attackers can pre-compute billions of hashes, rainbow tables, and quickly match them. So hashing is just the first building block. We need more. A salt is a unique random value added to each password before hashing. Every user gets a different salt, which prevents two identical passwords from producing the same hash. This means rainbow tables become useless because each hash is unique, even if users chose the same password. Salting is essential, but still not enough on its own. Peppering adds another secret value, but unlike a salt, the pepper is not stored alongside the password. It is kept in a secure location, like an HSM or application environment variable. So even if a database is compromised, attackers still cannot verify cracked passwords without the pepper. It's an additional layer of defense that protects the system even when hashes are exposed. These algorithms are designed specifically for password hashing, not general hashing. They are slow by design, making brute force attacks extremely expensive. Bcrypt uses adaptive work factors, cost values, forces attackers to spend significant time per password guess. Still widely used and trusted script, memory hard algorithm, much harder for attackers to parallelize cracking using GPUs, ASICs, Argon 2, the modern standard. Winner of the password hashing competition. Highly configurable, memory time, and parallelism. Best defense against modern hardware-accelerated attacks. Public key cryptography uses a public-private key pair to enable secure communication, identity verification, and trust between parties who have never met. It allows one key to encrypt and the other to decrypt, or to verify signatures created with the private key. This is the core of TLS HTTPS, certificates, SSH, blockchain addresses, and secure messaging systems. Digital signatures use public key crypto plus hashing to give us three powerful guarantees. Integrity. The data wasn't changed authentication. We know who signed it, non-repudiation. The signer can't deny it. Digital signatures are used in code signing, blockchain transactions, certificates, smart contracts, and secure documents. Hashing is a one-way, irreversible function that converts data into a fixed-size output. Even the smallest change produces a totally different hash. Hashing is essential for integrity checking, digital signatures, block linking in blockchain, secure password storage, and verifying large datasets efficiently. Merkle trees build on hashing to create a hierarchical cryptographic structure where every leaf is a hash of data and every branch is a hash of the hashes below it. This allows efficient integrity verification, tamper detection at massive scale, quick proof of inclusion without exposing all data. This is how blockchains verify entire ledgers without downloading everything. It's also used in software integrity, distributed systems, and secure file synchronization. PGP and GPG are decentralized, user-controlled encryption systems. They use public key cryptography to allow people to encrypt emails, files, and messages, or digitally sign what they send. A key feature is the web of trust model. There's no central authority. Users validate each other's keys manually or through trust networks. This gives individuals and organizations maximum control over their keys, which is why PGP-GPG is popular in cybersecurity communities, open source ecosystems, and environments where privacy is critical. Yes, MIME also uses public key cryptography, but it relies on PKI and certificates issued by trusted certificate authorities, CAs. This makes it ideal for organizations that need enforceable identity assurance, such as government, finance, healthcare, and enterprise environments. Because SMIME uses X509 certificates, everything integrates cleanly with corporate email systems, Exchange, Outlook, Gmail Enterprise, and provides strong policy enforceable identity. Both PGP, GPG, and SMIME support end-to-end encryption, ensuring only the intended recipients can read the message. Encryption protects confidentiality, whether the email sits in an inbox, travels across the internet, or is stored on a server. Digital signing ensures authentication, you know who sent it, integrity, the message hasn't been altered, non-repudiation, the sender can't deny it. Signatures are critical for verifying software updates, financial communications, legal documents, and any sensitive email exchange. BitLocker is Microsoft's built-in full-disk encryption solution for Windows. It uses AES encryption and typically relies on the TPM, Trusted Platform Module, to securely store keys, ensuring the device won't boot into the OS unless the system integrity checks pass. BitLocker is widely deployed in enterprise environments because it integrates smoothly with Active Directory, Intune, and compliance policies. It's essential for securing Windows laptops, especially for mobile or remote employees. FileVault is Apple's native full-disk encryption for macOS. It uses XTS AES-128 with a 256-bit key and integrates tightly with Apple's secure Enclave and OS-level identity systems. FileVault is seamless for users. Once enabled, encryption and decryption happen automatically in the background. Quantum computers pose a real threat to today's public key cryptography. Algorithms like RSA and ECC could eventually be broken by quantum attacks, especially Shor's algorithm. Post-quantum algorithms, or PQC, are new cryptographic methods designed to be resistant to both classical and quantum attacks. NIST is already finalizing new standards, including Crystal's Kyber for key exchange and Crystal's dilithium for digital signatures. Over the next decade, these algorithms will become essential for protecting long-lived data, critical infrastructure, and national security systems. Homomorphic encryption is one of the most exciting developments because it allows data to be processed while it is still encrypted. That means a cloud provider can run analytics without ever seeing the raw data and without decrypting anything. This is a game changer for industries like healthcare, finance, and government where data sensitivity is high, but analytics are critical. A zero-knowledge proof allows one party to prove that something is true without revealing the underlying data. For example, proving you're over 21 without showing your birth date. ZKPs are used in privacy-preserving authentication, blockchain scalability, digital identity, confidential transactions. They are essential to emerging privacy-centric architectures and Web3 systems. Secure multi-party computation allows multiple parties to collaborate on computations without exposing their private data to each other. No single party sees the full input, yet they can compute a shared result. Use cases include joint analytics between organizations, fraud detection across banks, collaborative medical research, privacy-preserving AI models. SMPC is a key technology enabling collaboration without sacrificing confidentiality. Thank you all for joining me for another episode of Technology and Cybersecurity Explained. I wish you the very best in all your future endeavors, both in your studies and in your professional paths. Until we meet again, stay curious, stay innovative, and stay secure.